Hi, this is Melanie Fine of Chem and 10, and today we're going to talk about Newton's law of gravitation. So Newton's law of gravitation is that the force of gravity in newtons is equal to this universal gravitational constant called G, capital G, and that's equivalent to 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. You don't need to memorize this number, you just need to be able to use it in this equation whenever it comes up. So it's equal to so we've got the force of gravity is equal to this gravitational constant G times the mass of one object times the mass of another object. Both of those masses are in kilograms, divided by r squared, which is the distance between those two objects in meters squared. So any two objects in the universe exert a gravitational force of attraction between them. Because G is so small, and generally masses of, let's say, human beings are so small, that that the force of gravity that we feel is negligible. It's on the order of, let's say, 10 to the negative 11 or 10 to the negative 10, which means that the decimal is all the way 10 spaces to the left. So any two objects exert a gravitational force. Again, we don't feel it between people, but when we deal with something as massive as a planet, like the planet Earth, we feel that gravity, and that's the gravity that keeps us on Earth. That's the gravity that is our weight. That's the gravity that makes things fall when we drop them. So large masses, you can notice this gravitational force, even though any two objects exert a force on each other. So the force increases based on increased mass. If you have a large mass, you're going to have a large force. But it's inversely proportional to the distance between them squared. This is also known as the inverse square law, which means that the larger the distance between them, the smaller the force. Because notice R is in the denominator. So the larger R gets, the smaller the force. Let me give you an example. If R is 2, right? Let's say r squared is 2. Even if let's do it this way. If the distance between two objects is 2 meters, then we have a force of gravity that's 1/4. Okay? I'm leaving out the masses and the gravitational constant just to prove a point. Let's say that you increase the distance between them to 3 meters, okay? So you've got two people that are 2 meters apart. And then let's say this guy then moved to, I hope you're appreciating my beautiful drawings here, moved to 3 meters apart. Is the force going to be stronger or weaker? Well, we know from magnets, etc., which it's not the same thing, but we can understand it, that as they get further apart, that force is going to weaken. That force is going to get less. And let me prove it to you. Remember when they were 2 meters apart, it was 1/4. When it's 3 meters apart, it's 1/9. 1/9 is a smaller number than 1/4. If it's 4 meters apart, it's going to be 1/16, etc. So the greater the distance between the objects, the less gravitational force they feel. So two objects feel. So gravitational force is a function of two things: the masses of the objects and the distances between them. So let's look at a sample problem. We're also going to have to use our calculators to do the scientific notation. Okay, so determine the force of gravitational attraction. So what they want to know is Fg between the Earth, which has a mass of 5.98 times 10 to the 24th kilograms, and a 70 kilogram physics student, if the student is standing at sea level, a distance of 6.38 times 10 to the 6 meters from Earth's center. Why are they saying sea level? Well, they want us to know that this person is at level with the Earth. They're not standing on top of a large mountain like Everest, which would add more distance between that person and the center of the Earth. So here, and we know that this distance, r, is equal to 6.38 times 10 to the 6 meters, okay? So our equation is Fg equals capital G m1 m2 over r squared. I'm going to plug in my numbers here. G, again, is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Remember, the difference between science and math is that these aren't pure numbers. These numbers represent things in measurement, so they have units. So we always need to keep the units. The mass of 1, let's say that's the mass of the Earth. It looks like we're going to run out of room here. I could have let the physics student be, see, I told you I'm going to run out of room. I could have let the physics student be the first mass and the Earth be the second mass. It doesn't matter. There's some law of math that says whichever one you multiply first, you're going to get the same answer. So I'm just going to spread this out a little bit, times a 70 kilogram physics student, right? And then I'm going to divide that whole thing by r squared. What is r? R is 6.38 times 10 to the 6 meters squared. Okay? So let's do the math. Here's my calculator. I'm going to take 6.67, and to do scientific notation on this calculator, I need to use that EE key. That EE key replaces the times 10 part. And since it's raised on this blue, right, it's raised, you see that above the x minus 1 key, and it's blue or purple, I need to press that blue or purple function to get to that. And then I am just going to place negative 11. Remember, you don't use the minus sign. Oops, you didn't see that, did you? I used negative 11. You're not going to use the minus sign for negative, only for subtraction. I'm going to multiply that by 5.98. Again, EE, in this case 24, so second EE, 24. And then I'm going to multiply that by 70. That's my numerator. I'm not finished because now I need to divide by 6.38 times 10 to the 6 meters squared. So I'm going to actually put this in parentheses because I'm going to square it. If I weren't going to square it, it should be that a calculator knows that, remember PEMDAS, it does parentheses first, then exponents. So it should know to do the exponents before the division. But I'm not so sure in scientific notation if that's the case. I'm concerned that squaring might just square the exponential, the 10 to the 6. I could be wrong, but I'm just going to do parentheses just in case. 6.38, again, scientific notation. I'm not pressing times 10, I'm just pressing that EE key to the 6th power, close parentheses, and I'm going to square it. And the square button is right here. Do you see that? So I'm going to press that. That's going to square my denominator. I press equals, and that is my answer. And I'm going to round to 2 decimal places. So I'm going to round to, well, I've got 685 point. So the 100th place, which is what I want to round to, is a 393. But I always look 1 digit past. Does the 6 round up to 3? Yes, it does. So that's going to be 0.94. And then you always want to put your answers in units. So how do you decide what units to use? You look at what doesn't cancel out. So here, meters squared canceled out. Kilograms squared canceled out because kilograms times kilograms is kilograms squared. What's left over is newtons. So that is our answer, 685.94 newtons. So that's how you solve for the force of gravity. Let's look at how to manipulate this equation to solve for something else. We'll go on to the next equation. Excuse me, the next problem. Determine the mass in kilograms of a football player whose gravitational force is 980 newtons. So that's Fg. They've already given us Fg. The mass of the Earth, okay, that's M1, let's say. I guess we want to know what is the mass of the football player. Again, I could have named the football player mass 1 and the Earth mass 2. It doesn't matter. And its radius is this, okay? And again, we're going to assume our friend is at sea level. Our equation is Fg equals capital G m1 m2 over r squared. But before I go on, notice that I want to solve for M2. I'm just going to write that in red, okay? So I need to isolate that variable. I need to get M2 by itself. And right now it's accompanied by G, M1, and R squared. To get M2 by itself, to isolate the variable, I need to divide by whatever's in the numerator to cancel that out. So actually, let me use a different color. I'm going to divide by G and M1 so that G and M1 cancel out. And then I'm going to multiply by R squared so that R squared cancels out. Now, as I'm sure you're aware, I can't just do that. But if I do it, if what I do to one side I do to the other side, then it's all good. So I'm going to multiply on the left-hand side R squared divided by G M1. Okay? So our equation becomes M2 equals FG R squared over GM1. And now I just plug in my numbers. FG was given to us as 980 newtons. R squared, R is 6.38 times 10 to the 6 meters. And of course, because it's R squared, we're going to square that. All divided by capital G, which again is a constant that you just need to be able to use. 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. Units matter. Times M1. And M1 we said was the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. So we're going to put this in our calculator. Okay, so I've got 980 times, and this is scientific notation. Again, I'm not sure if it's going to square the whole thing or just the exponential. I haven't tested it yet, so I'm going to put this whole thing in parentheses and then square it. 6.38. Remember, in scientific notation, you don't put in times 10. You just use that EE or that EXP button, whatever your calculator has, to the 6th power, close parentheses, and then square it. Okay, I'm going to divide by 6.67 EE negative 11. Oops, you don't see that. I used this negative sign down here, negative 11. And then you would think that I multiply by 5.98 times 10 to the 24, but that's not what the calculator knows. When I multiply by this number, it doesn't know that that we're still in the denominator. So it's going to think that 5.98 times 10 to the 24th is up here in the numerator. So to tell the calculator that this is in the denominator, we're going to have to divide again. It's sort of like a serial division, a division and then a division. We're going to divide by 5.98 EE 24. Press enter, and that is our answer. Our answer is, and let's round it again to the hundredths place. So it's 100. The hundredths place is the place, so 0 is in the tenths place, and this 0 is in the hundredths place. We don't just cut it off there. We look one digit past at the 9, and we ask ourselves, does the 9 round up to 0? Well, of course it does, right? And then what are the units? Let's cancel them out. We've got newtons and newtons. Meter squared, kilogram and kilogram squared. Notice that kilogram only cancels out one of the kilograms squared, not the other. So our units are going to be, notice their units are in the denominator of the denominator, which is the same thing as saying that the units kilogram is in the numerator. And let's do one more problem. This problem we're going to solve for distance. Okay. Determine the radius in meters of the moon if a 70 kilogram chemistry student on the moon experiences a gravitational force of 117 newtons. Remember, when we have the newtons, that's force of gravity. And this is the mass of the chemistry student. Let's say it's mass 1. And we have the mass of the moon as m2. Again, it doesn't matter which one's m1 and which one's m2, as long as you stay consistent. So our equation is always Fg equals the universal gravitational constant, capital G, m1, m2 over r squared. We want to solve for r. Well, we want to solve for r, right? We want to solve for r. I'm just going to put the squared there. It's green too. This is the hardest type of problem because students always have trouble, or not always, I shouldn't say always. Students often have trouble when they're solving for an unknown in the denominator because they don't take the number out of the denominator. Don't solve for a number in the denominator. Get it out of the denominator. The closest way, the best way I know to do this is to cross multiply. And what does that mean? You multiply this denominator times this numerator. So I get Fg times r squared equals, and then I take this denominator times this numerator. And we know that any number times 1 is itself, so I'm not going to write the 1. Well, maybe I'll write it just to be clear. And I would multiply that by 1, right? But any number multiplied by 1 is itself. So now I'm not finished, but I have gotten r, the distance, out of the denominator. So remember what we did last time. To get the number out of the denominator, we wanted to isolate the variable. We want to isolate r squared. Right now it's being multiplied by Fg. So the way to isolate it is if it's being multiplied by Fg, we need to divide by Fg. And generally you can't just do this unless you do the same thing to each side. So Fg cancels out, and we end up with r squared is equal to G m1 m2, again, multiplied by 1 is itself, all over Fg. But wait, there's more. Because it didn't ask us to determine the radius of the radius squared of the moon, it asked us to determine the radius of the moon. And this answer is going to give us the radius squared. So how do you go from squared to unsquared? You take the square root. So I need to take, let me use a different color. I'm going to take the radius, I'm going to take the square root of the radius so that I end up with just r. But if I'm taking the square root of one side, know that I have to take the square root of the other. Okay, so our equation becomes r is equal to the square root of gm1 m2 all over Fg. So now we'll plug in our numbers. We're going to get to use a lot of our calculators in this problem. Okay, so that's equal to, I'll do the square root at the end. G, remember, is just a constant, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. M1, I said, is our 70 kilogram chemistry student, and M2 is the mass of the moon, 7.34 times 10 to the 22nd kilogram, all over Fg, which they told us was 117 newtons. And remember, don't forget, easy way to make a mistake here, we're going to have to take the square root of the entire number. So we can do it this one of two ways in our calculator. We can take the square root initially and put everything inside the square root equation, or we can do the square root at the end. I'm going to take the square root at the end. It just seems a lot easier. So I'm going to take 6.67. Remember, I don't do times 10. I do the EE key times, I always hide that negative sign, times negative 11 times 70 times 7.34 EE22, all divided by 117. And I press enter. And people will make the mistake and put this as the answer, but remember we have to do one more thing. We have to take the square root. In this calculator, the square root is the same thing as, oh, here it is. The square root is on top of the x squared. So the square button and the square root is that purple above it. So I'm going to have to do the second this. Oh, it's not going to let me do that. Okay, so let me see if I can go back. I'm going to instead press enter. I had that answer. Okay, and then maybe it would have been better to put the square root first, but what I'm going to do is I'm going to save this number. So I'm going to store it. You see that store? I'm going to save this answer. I'm going to save it as A. So I'm just going to press enter. Okay? And then because apparently I cannot do the square root and then add the number. I can't have the number and then do the square root. I need to do the square root first, apparently. And then I'm going to paste that number. So I have to use recall instead of store. So I'm going to go second recall. Remember I stored it as A, so I'm just going to press enter. And then I'm going to enter. And that is my answer. My answer, the square root of that, looks to be a big number because I'm going to actually put this into scientific notation. It's still round to the hundredths place of scientific notation. So let me just write it first in decimal form, standard notation, 1711461.11. We'd look at the 4 and see if that rounds up the 1. It doesn't. But to put this into scientific notation, remember for scientific notation you need the decimal to be between the first two non-zero digits. So I need to move this back 1, 2, 3, 4, 5, 6 spaces. So it's going to end up being 1.71. Again, I'm rounding in this case to the hundredths place in my significand. This part of the scientific notation is called a significand. Okay, that second one does not round up the first one. And remember, I moved it back 6 spaces, so I'm going to have to write times 10 to the 6. That is my answer, almost, but I don't have units. So let's see what units cancel out. The newtons cancel out. Kilograms squared cancels out from both kilograms. So my units are meter squared, but remember we took the square root. So the square root of meter squared is simply meters. And there you have it. That's how to manipulate Newton's law of gravitation to solve for gravity, the force of gravity, to solve for mass of any of the two objects, or to solve for the distance between the two objects. I hope you enjoyed this video. This is Melanie Fine.